This series of demonstrations is going to allow you to practice these double replacement precipitation reactions. So I encourage you to stop the video and try these for yourselves and then look at how I work them out. In this series of demonstrations, we're going to look at double replacement precipitation reactions. Now, they all have the same thing in common. Let me use a metaphor to try to help you understand once again. So imagine you have two sets of couples. Let's call them Larry and Jan and Dawn and Mabel. They are just friends, best of friends. They each get invited to a Friday night dance, and they don't have a significant other. They don't have anybody that they're romantically involved with, but they do like to dance. So they decide to go to the dance together. There is a point in the dance in which the host gets up and decides to do a square dance. Now, in a square dance, inevitably, partners are supposed to switch sides, are supposed to switch partners. So when this happens, of course, what you get is Larry and Mabel coming together, plus Dawn and Jan coming together when they switch partners. So when this happens, there is magic that occurs between Larry and Mabel. Okay? Larry just looks down on Mabel. Mabel looks up at Larry, and there's just, you can hear romantic music in the background. So they split back up, and as the night continues, Larry decides to say to Jan, "Hey, Jan, I'd like to go and ask Mabel to dance. I don't think that Dawn is actually dating Mabel." So Jan goes, "Go for it." And he says, "Well, what about you and Dawn?" And she goes, "No, not really interested." So Larry goes and dances with Mabel all night long. And from there, we have the start of a romantic, beautiful relationship. So, if we were to apply chemistry concepts to this, we would say that Larry and Jan are an aqueous solution. So, if we could see this aqueous solution, we would see a bunch of particles, a bunch of Larrys and Jans and Larrys and Jans and Larrys and Jans. And because they're just friends, whenever they do come together, they just split apart. There's no magic, there's no romance. They are just simply friends. On the other side, we have Dawn's and Mabel's, Mabel's and Dawn's, Dawn's and Mabel's. And they too are just friends. So if you were to look at both solutions, they would look absolutely clear. You wouldn't be able to tell that there's anything in them because we are in ion form. And ions are about the size of an atom, and you can't see atoms. So typically a double replacement reaction involves two clear solutions. Sometimes they'll have a color, sometimes they don't. Key thing is you can't see anything inside of them. And then you pour them together and something magical happens. You will still see Dawn and Jan, not Dawn and Jan's. Yes, I was right. Dawn's and Jan's floating around. And nothing really happened between these two. They met, they briefly danced, but there was just no sparkle. There was nothing there. But what you're going to find down here is a pile of Larry and Mabel's. Because when they meet, they come together to form crystals, and those crystals will grow on each other until finally you have what appears to be crystals forming, and eventually they will settle out. So let's look at the first of these demonstrations by looking at what happens when Mercury II nitrate and sodium carbonate meet up. Notice that you have two clear solutions. They don't appear to have anything in them, but when they mix, without a doubt, something happens, and those are crystals that are forming there. All right, so here we go. Mercury 2, right, plus 2. Nitrate is -1, so I'm going to need 2 of them. I'm going to get rid of my charges. Don't need any charges in the final equation. And these are solutions. As you saw, they were clear. You couldn't see anything. So they were aqueous solutions. So obviously mercury and nitrate were together, but they were not together. They were just friends dancing. In the other test tube, you have some sodium +1, carbonate -2. So you're going to need 2 sodiums. Get rid of the charges. And they too are just dancing. They're not romantically involved. So if you take out your solubility chart, you need to check, will mercury precipitate with carbonate? Will mercury and carbonate be a couple? Are they insoluble? Well, according to the solubility song, carbonates are basically all insoluble unless they are bonded to an alkali metal like sodium. So carbonates tend to be solids unless we're talking about potassium carbonate or sodium carbonate or lithium carbonate or even ammonium carbonate, which is a polyatomic ion that's similar to the alkalis that are always soluble. Sodium and nitrate, no. Alkalis, that first column, sodium, potassium, lithium, no. They will never, ever form a solid. Nitrate are as soluble as can be, according to the song. They will never, ever form a solid. So, our molecular equation is going to look like this. HgNO3 2 aqueous plus Na2CO3 aqueous yields. Mercury goes with carbonate. Mercury is +2, carbonate is -2. So it's perfect. Perfect. Plus sodium goes with nitrate. Now, we got these little 2's. Let's go back a second. This little 3. Always ask yourself, because this can be kind of confusing, is the little 3 always with carbonate, or is it there only because it's bonded to sodium? No. Carbonate is CO3. That little 3 is always with carbonate, so it goes across completely. Okay? This little 3, is it always with nitrate, or is it there only because of mercury? No, it's always with nitrate. So that has to go across. This little 2, is it always with nitrate? Every time you see a nitrate, you see a parentheses and a little 2? No. It is there in order to balance out with mercury. So we may or may not need it on the other side. We need to make sure we have correct chemical formulas. So +1, -1, according to the chart. No, that's it. Okay? They didn't do anything. They were just friends afterwards. So we put down aqueous. Okay? So, if something's bothering you, it's probably, you have every right to be bothered because, what happened to the 2 there? Okay, we have to account for that. But we can't account for it by taking it over and making it into a little 2 here. No. No. NaNO3 is a correct formula. Leave it like that. We do need to balance it. We balance it with big numbers. So if a little number is always with those elements, then they stay little. If a little number is there only temporarily in order to balance things out, then they become a big number on the other side. So now let us write a total ionic equation. Because the way it's written now, it looks like we have two couples. We don't have two couples, do we? In reality, we had a mercury ion, and once again, temporaries become bigs. Two nitrate ions. Temporary becomes big. Two sodium ions. Plus, no, this is not a temporary. It stays little. CO3 negative 2 aqueous yields. That's a solid. They did become a romantic couple. So you leave them together. But the others are still individuals. And you have to distribute that two throughout. So it's two sodiums and two nitrates. If you've done this correctly, there should be two sets of ions on either side that are exactly the same. Nothing really happened. And that would be Mr. Sodium here came to the party as just the friend of carbonate and leaves as just a friend. Nothing really happened. And Miss Nitrate here came as a friend and leaves just as a friend. We call those spectator ions. Spectator ions. So a net ionic equation is going to just give you what really happened. What really happened is that mercury ions reacted with carbonate ions to form, as you saw, a brownish solid that precipitated down and settled down at the bottom. So what I did here is wait a day and let the crystals settle out, and you see all the crystals down at the bottom of the test tube. I really like this reaction because it not only gives you crystals, it gives you bright yellow crystals. Just a brilliant yellow crystal, which just makes me feel happy. All right, so what did we have here? Did you notice there were two super clear solutions? One contained lead plus 2, nitrate minus 1. So I'm going to need two of these things. Let's get rid of the charges. And it was clear there wasn't any solids, so that's an aqueous solution. Plus potassium plus 1, iodide minus 1. Okay, that's done too. There you go. And what happened? A yellow crystal formed. So the question is, was it lead iodide or was it potassium? Okay, stop. It can't be potassium anything. It can't be nitrate anything. Alkali metals are always soluble. Nitrate ions are always soluble. So that can't be it. You got to memorize that song. You got to. So what do we have on the other side? We have lead plus 2, iodide minus 1. What does the song say about iodides? Chlorides, bromides, iodides are soluble, but there's a secret I'm going to tell. Working in the lab, it's plain to see they're insoluble with silver, lead 2, and mercury 1. There it is. There it is. Okay, so we're going to need two of these things, and that is my solid. And potassium reacts with nitrate to do nothing. Okay, let's get rid of the charges. They should not be there, but we've got a problem. They're not balanced. You've got 2 nitrates here, only 1 there, so 2. 2 potassiums, 2 potassiums, and that fixes our little problem with the iodides, because now we have 2 I's and we have 2 I's. 2 I's. So that is called your molecular equation. Your total ionic equation is far more, first of all, it's longer to do and far more accurate. So you have lead ions, and the 3 with the, that's always permanent. The 2 is not, so the 2 becomes big. Nitrate ions plus 2 potassium, big stays big, plus 2 iodide yields PbI2. It's a solid. It stays together. Plus 2 ions of potassium plus 2 nitrate ions. Remember those charges. So, if we've done something right, there should be 2 sets of ions that are exactly the same on both sides. They encountered no change. They were aqueous to begin with. They are still aqueous at the end. So, the net ionic equation is some lead ions met up with some nitrate ions. I'm distracted. Met up with 2 iodide ions to form lead 2 iodide, that brilliant, brilliant yellow crystal. A day has gone by and you can see the yellow crystals have gone down to the bottom. This reaction is going to be Mercury II nitrate on the left, and on the right is going to be potassium iodide again. Notice it's first kind of like a pale orange, and then it turns into a really, really bright, deep orange. I don't know how to describe it, and it's kind of cool. Mercury II nitrate again. So we'll need 2 nitrates, and of course you saw the clear solution, so they were just dancing. They were just friends. Potassium, iodide, yep, just dancing. Okay, what are our choices? Well, it's not going to be potassium anything. Folks, get it through your heads. Potassium, sodium, lithium, cesium. It's just potassium and sodium. If you can just remember potassium and sodium, it's going to give you such an advantage. No, they are aqueous. They're aqueous, so it must be mercury and iodide, and you're going to need 2 iodides. And that's a solid. It was that orange crystal. Let's get rid of the charges, and of course potassium goes with nitrate. We don't bring that 2 across because that's a temporary 2. That's there just to balance with mercury. So we're gonna have to deal with that. That's gonna have to be dealt with, but it's dealt with like that. And of course that gets fixed right there if we put that potassium there, and now we have the right number of iodides. We're good. The total ionic equation is going to look like this: a mercury ion dancing. That little 2, is it there because of mercury, or is it there because it's always part of nitrate? No, it is there because of mercury, so it comes down as a big number. If you're big, you stay big. If you're big, you stay big. Don't forget the charges. The charges are important. Can't have an aqueous solution if it's not a charged ion. And then if it's a solid, it stays a solid. And of course, we should have two ions that are exactly the same on both sides that didn't do anything. So, chlorides, bromides, iodides are soluble, but there's a secret I'm going to tell. Working in a lab, it's plain to see they're insoluble with silver, lead, and Mercury I. But in this case, it's Mercury II, as you can tell. Mercury II also forms a solid. The song does not give us all of the insolubles, just the most popular ones. And here's one that's not as popular. But it has to work. We saw the crystals, and it cannot be potassium and nitrate. Even though at first a lot of crystals seemed to have formed, in actuality, it wasn't that many. Okay, so you saw that white crystal. Oftentimes, that white crystal is referred to in the medical field as a barium cocktail. Barium cocktail. That barium cocktail is going to be given to somebody that needs to have a CAT scan of their intestines. So what happens is they give this white, opaque, liquid milkshake type thing that tastes awful. Sometimes they try to add flavoring to it, but it doesn't help much. You're supposed to just down it. So that is a barium sulfate solution. It's going to be a suspension because the barium sulfate is in crystal form, and barium sulfate cannot be dissolved, so it's not going to enter into your bloodstream, which is a good thing because barium could do some nasty damage to your body. It's going to stay in your gut. So as it goes through your gut, it's going to coat it, and at a particular time, they've got it timed perfectly. They'll take the CAT scan, they'll take the series of x-rays, and what happens is the barium is so massive that it will be absorbed. The x-rays will absorb the barium, and they'll be able to get this really, really detailed picture of what your intestines look like, and down to all the little individual folds, and they can tell where the obstruction has taken place. So that white powder is barium sulfate, and barium sulfate is used in order to get very accurate pictures of your intestines without having to go in and put a camera down there. So, here we go. Barium is +2, chlorine is -1, so you'll need 2 of them. And they were a clear solution. Sodium +1, sulfate is -2, so you'll need 2 of these. And they were a clear solution. What was the solid? Well, it can't be that. Cannot be that. Okay, so your only choice is barium +2, sulfate -2. Okay, it's done. That white chalky solid is barium sulfate. Sodium +1, chloride -1. Well, what about the little 2? Okay, is the little 2 always with chlorine? And don't say that it's a diatomic. No. Diatomics are only when these 7 elements are by themselves in their natural state, gas, liquid, or solid, not aqueous. No, not aqueous. So no, that 2 is there because barium is +2. So it doesn't go across. This 2 is here because sulfate is -2. So it doesn't go across. Now, that's done. You know that NaCl is correct. But there's something bothering you, and it should be bothering you, because if you have 2 NAs there, you need 2 NAs here. If you have 2 Cls here, you need 2 Cls here, and now it is balanced. Molecular equation, Ba plus 2. Is that there because, yes, that's there because of barium, so it comes down as a large number. This is there because of sulfate, so it comes down as a large number. Two Na plus, 2 Cl minus, and of course they are your spectator ions. Your final answer, Ba plus 2 plus SO4 negative 2 forms BaSO4 solid. You will notice the bright blue color of copper 2 chloride. That is distinctive for copper. So whenever you see that color, think copper. So that bluish crystal that is formed, it looks almost like a gel. Probably would be categorized as a gel, which is a special type of solid. Copper plus 2, of course, Cl minus. So I'll need 2 chlorides, and that was a clear solution. So it's aqueous. Sodium plus, carbonate minus 2, Na2CO3. Can't be sodium. Copper carbonate, what does the song say about carbonates? Carbonates are largely insoluble. They will form solids unless, of course, we're dealing with an alkali metal. So it's Cu plus 2, carbonate minus 2. Yep, that's it. Solid plus, and we've seen this before in the last example, NaCl. Okay, so what really happens? Copper ions meets up with carbonate ions to form copper carbonate plus a bunch of ions just floating around doing nothing. So we call them what? What do we call them? Spectator ions. Spectator ions. Final answer. All right.